Hi everyone. In this session, we'll try to solve problems using radiation shields. Theory about radiation shields we already discussed in one of my previous lectures. Before proceeding to solve problems using radiation shields, I will try to solve one problem without shield. Then we'll proceed to radiation shields. A pipe of outside diameter 30 centimeters having an emissivity of 0.6 and at a temperature of 600 Kelvin runs centrally in a brick duct of 40 centimeter size square section having an emissivity of 0.8 and at a temperature of 300 Kelvin. We have to calculate the heat exchange per unit length of the pipe. Let us try to understand the problem. There is a pipe having a diameter of 30 centimeters, emissivity epsilon 1 as 0.6 and at a temperature of 600 Kelvin. It is running centrally inside a square duct made of brick whose temperature is 300 Kelvin and whose side is A is equal to 40 centimeters. We have to calculate the heat transferred between the pipe and the brick surface. We can treat this problem like concentric cylinder problem. Instead of cylinder in the outer portion, we have square duct. Only the area, surface area will be different. Otherwise, procedure is the same as what we used for concentric cylinders or concentric spheres. So, what is given in the problem? Diameter of the pipe capital D1 is given as 30 centimeters, that is 0.3 meters. Emissivity of the pipe epsilon 1 is equal to 0.6. Absolute temperature of the pipe capital T1 is equal to 600 Kelvin. And the side of the square section, brick section, small a is equal to 40 centimeters, that is 0.4 meters. And emissivity of the brick duct epsilon 2 is 0.8 and its temperature capital T2 is equal to 300 Kelvin. We have to find out the heat exchange between the pipe and the brick duct. We know this is the formula for heat transfer. Epsilon bar into sigma into A1. A1 is area of the pipe, surface area of the pipe, multiplied by T1 power 4 minus T2 power 4. So for concentric spheres or cylinders, the formula for epsilon is this, that is 1 by epsilon 1 plus A1 by A2 into 1 by epsilon 2 minus 1. Here A1 is the area of the pipe, that is pi into D1 into length of the pipe. Length we are assuming as 1 meter. Diameter capital D1 is 0.3 meter. If we substitute, we will get A1 as 0.9425 meter square. And A2 is the surface area of the brick duct. It is a square duct. So 4 times the side, 4 into A into length of the brick duct, L2. L2 we are taking unit length, so 1 meter. So 4 into A is 0.4. So 4 into 0.4 into 1. That comes to be 1.6 meter square. Now you substitute A1, A2, epsilon 1, epsilon 2. You will find out that epsilon bar is equal to 0.5513. Now you substitute the value of epsilon bar in the heat transfer formula. So Q is equal to 0.5513 is epsilon bar, then next is sigma, and then area A1, and then T1 power 4 minus T2 power 4. Finally, you will get heat transfer between the pipe and the brick duct is Q is equal to 3579.48 watts. Okay. Now, we will try to solve problem using radiation shields. The problem says, emissivities of two large parallel plates maintained at 800 degrees Celsius and 300 degrees Celsius are 0.3 and 0.5 respectively. We have two large parallel plates. This is plate 1. Its temperature is 800 degrees Celsius. The other one is at 300 degrees Celsius. Emissivity epsilon 1 of first plate is 0.3 and that of the second plate is 0.5. We have to find out the net radiant heat exchange per square meter area for these two plates. So we have to calculate the heat exchange between these two plates assuming unit area. Right. In the second case, find the percentage reduction in heat transfer when a polished aluminum radiation shield of emissivity 0.06 is placed between them. First case, there is no shield, we'll calculate. In the case 2, we introduce a shield in between whose emissivity is 0.06. That is epsilon 3 is emissivity of this shield. Epsilon 3 is given as 0.06. So it will be at a different temperature T3. Now we have to find out the heat transfer between plate 1 and plate 2. And finally we have to calculate the temperature of the shield. T3 we have to calculate. T1, T2 given, epsilon 1, epsilon 2 given, epsilon 3 is also given. We have to find Q without shield and then with shield we have to calculate, and then finally we have to calculate reduction in percentage reduction in heat transfer and temperature of the shield also. First we will consider the case without radiation shield. So formula for heat transfer between two parallel plates is epsilon bar into sigma into A into T1 power 4 minus T2 power 4. So epsilon bar, the formula for parallel plates is 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Substitute epsilon 1 and epsilon 2, you will find that epsilon bar is 0.231. Now you substitute the value of epsilon bar and you can find out heat transfer as 15,933.90 watts per meter square. This is a heat exchange between the two plates in the absence of radiation shield. Now we will proceed to calculate heat transfer in the presence of shield. So what is asked is percentage reduction in heat transfer because of the shield. So percentage reduction in heat transfer is equal to heat transfer without shield minus heat transfer with shield divided by heat transfer without shield multiplied by 100. Okay. So important thing we have to remember in the case of shield is whatever heat is transferred from plate 1 to shield, the same heat is transferred from shield to plate 2. That is a very important relationship. That's what I am putting here actually. So Q1 to 3 must be equal to Q3 to 2 actually. It's a very important relationship we should understand so that we will be able to solve the problem correctly. Right. First let us try to calculate what is Q1 to 3. So Q1 to 3 is epsilon bar into sigma into A into T1 power 4 minus T3 power 4. Now let us calculate epsilon bar for these two surfaces, that is plate 1 and shield. That is equal to 1 by epsilon 1 plus 1 by epsilon 3. Epsilon 3 is shield minus 1. To substitute epsilon 1 and epsilon 3, you will find epsilon bar is equal to 0.0526. Now we calculated between plate 1 and the shield. Now we will proceed to calculate the heat transfer between the shield and the plate 2 actually. So that is epsilon bar into sigma into A into T3 power 4 minus T2 power 4. Right. Here epsilon bar we are trying to calculate between the shield and the plate 2. So epsilon bar is equal to 1 by epsilon 3 plus 1 by epsilon 2 minus 1. You substitute the value of epsilon 3 and epsilon 2, you will get it is 0.0566. Okay. So we calculate between surface 3, shield and plate 2 actually. Right. Now we'll equate both Q13 and Q32. So this is what we get for Q1 to 3. Epsilon bar calculated between plate 1 and shield and sigma A are common. This is T1 power 4 minus T3 power 4. This side we calculate epsilon bar between the shield and the plate 2. That value we are epsilon bar we are substituting here. Sigma is common, and then T3 power 4 minus 573 power 4. That is T2 power 4. Now T3 is a only unknown. So epsilon and sigma and epsilon we can cancel. So only unknown is T3. We simplify it, we will get the temperature of the shield T3 to be 912.77 Kelvin. Understood? Now we have calculated the temperature of the shield T3. You substitute this T3 value either in the expression of Q13 or in the expression of Q32. You will be able to calculate the heat transfer between the two plates. I am substituting in the expression for Q13. So epsilon bar between 1 and a shield, sigma unit area T1 power 4 minus T3 power 4. So Q13 becomes 1883.16 watts per meter square. So this is the amount of heat transfer with shield. Now percentage reduction heat transfer is equal to, this is without shield, this is with shield, right? Comes out to be 88.18%. See, just by putting one shield, we are able to reduce the heat transfer by 88.18%. This is the importance of radiation shields in radiation heat transfer.